So we've covered velocity, unit tangent vectors, principal normal vectors. So now we want to get a little more interesting here and why we might think about those. Well, if we have acceleration, you can think of acceleration being kind of partly in the direction of your velocity, and that's pretty much what happens if you're driving down the road and you hit the gas pedal really hard, you just punch it, you feel that pull back, right? That's the acceleration. But there's also what we think of as a normal component. So you may be traveling with this tangent, but there's something that's pulling you this way. Think of that in the same idea of a car. When you sort of take the turn around a bank, you feel that centripetal acceleration. Sometimes we call it the centrifugal force. It's not really a thing, but there's the centripetal acceleration that's happening, that's kind of pulling. You're going this way, but you're being pulled that way. As you round the curve, your tangent vector is moving this way, but you have an acceleration that's moving kind of into the curve. So what we can do is we can break up acceleration into a vector that's only pointed in the direction of the velocity, or that's what we use, that tangent component. And then there's one that is broken up into that normal component. So we can call these the tangential and normal components of acceleration. So we can always break it into those two pieces. Now, in the case of a constant velocity magnitude, and that's a little different from constant velocity. If velocity is just a constant vector, well, then the derivative of a constant vector is 0. So that's not very interesting. But let's say that it's going the same speed, it may be in a circle. Well, then your acceleration is going to be fully normal to the velocity. You're basically going to always only have that centripetal component in terms of acceleration. So that's just something that's interesting to know, kind of helps you with some physical intuition. Anyway, so if we have some acceleration for a particle whose position is described by this position function r of t, then we can rewrite that as the sum of some number times the tangential component plus another number times the normal component. So we want to figure out what these what these coefficients actually are. And we do that with these formula. So A of t is, and you could use any of these, but as far as I'm concerned, it goes from less to more practical as you go along. So we could take the derivative of the magnitude of the velocity. So that's already kind of nasty, right? The magnitude of velocity isn't necessarily clean most of the time. So the derivative there may also not be that clean. But A dot t, that's probably decently clean. But this is probably the one you really want to do, right? You have a position vector. You're already going to get v because you have to get it to get a. And so then you just take the magnitude of v, you compute a dot product. Dot products are usually pretty easy. Divide it by magnitude, and there you go. And the normal component can get really nasty if you start at the left. You'd have to get t prime, when t prime is gross, right? So you don't want to get the magnitude of t prime or v. Well, then you have a dot n. Well, that's really not much better than this, if at all better. Now, this one's not too bad. Again, you already have to get v to get a. Getting the magnitude of v, if you've already done it for this piece, you already have the magnitude of v on hand. The problem is you have to compute a cross product, and cross product's going to, again, be kind of nasty. And then you have to take the magnitude of that cross product. So probably the easiest thing to do is this one, which is if you get the magnitude of a squared, which is just a dot a, which probably isn't that bad, and you subtract this number, which you already have to get anyway. So once you've got that number, you just subtract it from the magnitude here and take a square root. To me, this is the cleanest way to go. I would say use these two at the end. And again, that little normal piece is called the centripetal component because it relates to that part that that has to do with the curvature of the position.